Hi, everybody, and welcome to our live stream of the NG-15 ISS resupply launch out of NASA Wallops on the Katherine Johnson Antares launch vehicle. That's happening here in about 35 minutes. We're coming to you from Blacksburg, and most of us are remote and in our offices, so we appreciate you indulging us with being on this remotely. We hope to be able to host people live sometime in the near future. But I'm going to remove my mask because I am alone in my office. What we're going to do over about the next 35 minutes here, preceding the launch, is to meet the team, discuss the design and the build of our particular experiment. There's a number of experiments launching on the Cygnus today. And one of those was built here in Blacksburg at Virginia Tech called ThickSat. So we'll discuss the design and the build, the testing, the integration of that into the launch vehicle, the schedule, and you'll get an opportunity to meet the team. Please put questions into the chat. We'll answer your questions at the end after we transition to the launch feed. So you don't have to go anywhere or transition to a different YouTube feed. This will all be streamed live here. And then we'll come back and get to talk with the team, and we'll read the questions into the chat. So again, thank you all for joining. We're very, very happy that you're here. And I want to start with an intro to some of the space research that's going on here at Virginia Tech. So I'm John Black. I am the co-director of the Center for Space Science and Engineering Research here at Virginia Tech, and a professor in aerospace and ocean engineering. And I'm going to start a video here to tell you a little bit about Space at VT and some of the space research that we have going on here at Virginia Tech.
I like to tell employers in letters of recommendation that if you hire this person, in 6 weeks, you're going to be asking yourself how you ever got along without them. That's my goal. It's rare to have a student be able to design something, build it, test it, and we offer that opportunity.
I was working on the Raspberry Pi camera and I ran into some error and it completely crashed. Dr. Bailey just started laughing and he said, listen, this is not the sign of a stupid person. You've just found one way of not doing it right.
Learn the painful lessons here in the lab before you get to something in space. Testing is an art and you just gotta have experience.
We give the students things that are not part of a generic electrical or mechanical engineering curriculum.
You cannot survive without the ability to program.
You need solid computational skills, so you need to be good at math.
Real math, real problems.
Requirements flow, that means this, and this all have to come together to make it work.
You need to be good at physics.
Implementation, designing mechanical systems.
You need to be good at computer programming.
How to do a test.
We start from the design of the instrumentation.
How to build instrumentation.
They learn about what it takes to work things in space.
How to work with satellite systems.
How to know something is ready to fly.
So the numbers are no longer made up in a textbook. They really are, this is our orbit, this is our altitude, this is how fast we're going.
There is no one right answer. They have to figure out what a good answer is.
We produce students who get our employers to come back and ask for more.
Okay, so we don't do all of this all on our own. We have a lot of collaborators from NASA to the National Science Foundation to NOAA and companies all around the country. We have facilities all around the world. And right now we'd like to introduce our collaborators on ThickSat, which were our friends at NASA Langley Research Center. So I think Dr. Chamberlain is on. So thank you so much for being here, Matt. We appreciate it.
How about now? Can you hear me?
There we go.
All right. Hey, sorry about the delay there. Yeah, greetings from NASA Langley. I'm really excited about this launch today. Congratulations to all of you guys. I just want to take a couple moments to tell you about the relationship between the technology that we'll be seeing here on ThickSat and some missions that are ongoing at NASA Langley. So if you go to the next slide, over the last couple of years, NASA Langley has been developing deployable composite boom technology. By boom, I mean basically long, thin tubes, like the ones you see at the bottom right in this picture. These ones are made of very, very thin, compliant composite materials that allow us to flatten the whole boom and roll it up in a tight package that then out in space we can deploy, and we could build structures that way. So we can build antennas, we could build trusses, we could build, in our case, what we're most interested in doing is deploying solar sails. So these booms we've been developing over the last couple of years, and they're getting bigger. So originally, the ones that are going up on ThickSat were originally developed as potentially a replacement for metallic booms on a solar sail. We're moving up though, we're getting to a bigger one. So the ones you see in the middle of the bottom right picture will go on a mission called ACS-3. I'm going to tell you about more in a second. And then hopefully in the future, if ThickSat and ACS-3 work well, we'll move on to even bigger booms, like the ones in the far, far right, that will allow us to send very large solar sails with scientific instruments out into deep space. So if you go to the next slide, ACS-3 is the mission that we're working on very, very hard toward a late 2021 launch. We're partnering with Ames, NASA Ames, and Santa Clara University on a 12U spacecraft. So it's kind of the size of a very big coffee maker. Once out in space, it'll deploy solar panels and then a solar sail that'll be about 80 square meters. And the way it's deployed is that it pushes out composite booms like what you guys are flying on ThickSat. The ones on ACS-3 will be 7 meters long, and hopefully, if all works out, this will serve as a demonstration of the usefulness of this composite space technology for space missions. ACS-3 will go up to low Earth orbit. Hopefully, we'll be able to raise the orbit using the solar sail, lower the orbit, and steer a little bit. And if we do all that, we'll show that these composites are really useful. The next slide should show just a little bit of a video to give you an idea of how ACS-3 works. Everything here is pretty sped up. We deploy things pretty slowly generally in space, but you can see we'll probably be a rideshare payload, but a pretty big rideshare payload. So after being deployed and checking out and getting everything oriented correctly, we'll deploy solar panels, make sure our cameras and systems work. And then we'll begin deploying the solar sail. So what you see there is those black objects are the booms I've been talking about, very similar to what's on the ThickSat, but a larger cross-section. And those are going to be pushed out by motors, and they in turn will pull out our solar sail, which you see starting to come out now. And eventually it will come taut, and we will hopefully have a nice reflective surface, which we can use to catch light, which will propel our spacecraft. Okay, so on the next slide, I just wanted to reiterate, here at NASA, we're really excited about ThickSat for two main reasons. First of all, this is going to be the first in-space deployment of these deployable composite lenticular-shaped booms. They're smaller than what we would use on ACS-3 and have a slightly different layup, but still, we're excited to see how they behave after being stored for months. We're excited to see how your deployment system works. And then second, one of the things we're going to do on ACS-3 is the way we judge how well it's deployed, how straight it is, everything is with cameras, just like what you guys are using. So we'll be really interested to see how well you're able to track the boom that you guys are putting out. And we might learn something, and since we're still building ACS-3, we'll be able to implement changes between now and launch. So good luck, and if anybody has any questions, there's some contact information up there about the project and the overall program, and you can watch my colleagues deploying ACS-3 on the floor at NASA Langley. Good luck, guys. I'm really excited for you.
Great. Thank you very much for that, Matt. We appreciate it. And do you want to just say a few words about maybe some of the other composites and boom research that's been going on at NASA Langley and the integration with students and other universities?
Yeah, so we are, like I said, we're trying to grow up in scale. So exploring different layups, we're trying to grow these booms longer. At one point in time, the 7-meter samples that we sent you guys were the biggest we can do, and now we can go up to 50 feet, and we hope to get larger than that. The longer, these composites, they allow us to build larger, more stable structures in space compared to metallic structures. They're also just lightweight. So that's what we're excited to do, is to build these much larger, very stable structures that can either self-deploy, like yours is doing, or be driven out by a motor. Yeah, and we work with students all the time. We have students nearly all the time, even through COVID. We've had students working virtually. So yeah.
Great. Well, thank you again. We appreciate it, and it's been a great experience for the students over the last several years working with you folks. And thank you again for all the support up to now. And hopefully this can be one of a series of launches that we're able to do with VA Space and the other folks involved here. So while I have a second, I just wanted to thank our collaborators in addition to NASA Langley and Dr. Chamberlain and Dr. Fernandez and Dr. Wilkie. We also have worked extensively with several other organizations at Virginia Tech, including the Hume Center, the AOE and ECE departments. You'll see that we have students from several departments here that have collaborated over a number of years on this particular program. Also, the folks that are launching the experiment for us, VA Space, Near Space, Near Space Launch, Twig Space Labs, and the Virginia Space Grant Consortium and others. This has been a group effort over a number of years here. And with that, we'll transition to speaking to some of the students about their particular, the team leads for the various systems and subsystems of ThickSat to give you the overview of the entire experiment. So first up, I believe we have Rob, and Rob is going to be talking about the release mechanism.
Thank you, Dr. Black. I'm Bob Ingebertson. I'm a graduate student here at Virginia Tech, and my main job was to design the deployer that would release the tape spring. And in particular, unique to this mission is that the tape spring is designed to release on-powered. So instead of using motors, we only use the stored elastic energy from rolling up the tape spring. And just to show you the main design, the tape spring itself is a 80 centimeter long version of what was discussed by Matt. It's a thin shelled and a cross section resembling a circle that flattens out to create points on opposite sides. When bent along this wider axis of the cross section, it flattens itself, allowing it to easily be wrapped around a cylindrical structure, just like regular tape. Bending the tape string in this manner stores elastic energy, and the tape string will always try to restore itself to its original flat on-bent shape, which is something we can take advantage of that makes this deployment possible. The main components of the deployer include the structure, broken up into 4 parts that attach, a central spool that the tape string is wrapped around, and 5 rollers, 3 of which surround the spool and 2 which guide the deployment of the tape string out of the spacecraft, as well as a servo and 2 devices that can help confirm tape string deployment. There are also 12 ball bearings that are attached to the rollers and the spool to ensure that they can spin as freely as possible. Now, when the constrained energy is released, the tape string will try to expand outwards in all directions in an attempt to straighten itself. This expansion will be constrained by these rollers, which will only allow the tape string to expand a few millimeters. The rollers will then act as a low friction contact point that will redirect the spool's deployment in one direction by allowing the spool to spin and unwind the tape string. This deployment should be relatively fast with no motors and only take about a few seconds. More importantly, the tape string must be prevented from deploying until it is time to do so. The deployment is prevented primarily by the servo, which has a small arm that fits itself into one of 16 rectangular slots on one side of the spool and prevents the spool from rotating, which in turn prevents the tape string from unwinding. But this alone is not enough because the tape string can still unwind itself slightly by holding in the tip of the other end of the tape string. Should this tip of the tape string be brought in more than a couple of centimeters, it'll go beyond these 2 rollers at the front and then get stuck in the spacecraft, and that would prevent any future deployment. For this reason, the tape spring has a cover that will get caught by the sides of the deployers when it is fully pulled back and prevent any more inward movement, but it won't get into the way of deployment in the proper direction. And when we constrain the tape spring in such a manner, it also creates a small amount of tension, which during testing proved to result in more reliable deployment. With both ends of the tape spring constrained at the spool and at the tip, there's no way for the tape spring to move until the servo arm is commanded to rotate out of the rectangular slot on the spool, removing the constraint. Also attached to the deployer, we have the two main systems that are used to confirm the deployment. The primary one is the camera, which has been positioned to capture the entire length of the tape spring. And we have a secondary system in the encoder, which is attached to the shaft of the spool and can count how much the spool has rotated, which we can then match with the expected number of rotations for deployment. And that is how our deployer works. I will now turn this over to Derek, who can talk about the main ThickSat structure.
Okay. There we go. Yeah, so I'm Derek Whited. I'm a master's student in aerospace engineering here at Virginia Tech, and I oversaw the chassis development, so the frame of the satellite, and then a lot of the structural integration leading up to assembly, so fitting all the parts together in CAD and then in real life. So as Dr. Black mentioned, the development timeline was multi-year. So our first revision for the chassis came out of the senior design group that originally started the project back in spring of 2019. Once they were done, they handed it over to this group that's been presenting to make further changes prior to launch. So out of their first revision, we had a lot of learning lessons, including manufacturing tests that needed to be worked through. So the follow-on team made some initial changes, which included going to multiple parts instead of a single part. And that was over summer of 2019. In fall of 2019, we continued to make minor changes to the chassis as other parts of the satellite were being adjusted. And then in spring 2020, we actually had our third and final revision made with major changes just to meet all of the standards that were set by Near Space Launch and all of our other partners. So following the final revision being completed and checked out, this past summer in 2020, we did the manufacturing portion. So we had the chassis pieces milled at a local machine shop and then anodized as well in Roanoke. And then in October, we went through test and final assembly of the entire of the chassis and the entire satellite, and packed and shipped it to NSL in Indiana. So it's been sitting packed up for quite a while. But on the left-hand side here, you can see what a normal ThinSat chassis from NSL looks like. This is called a 1T. This would be the standard configuration for launch. On the right-hand side here, you can see the first revision that was delivered by the senior design team, and that's a 1T plus 5T. So instead of being an integrated chassis, you would have the original 1T with a 5T attachment with our deployer payload. So that's denoted by the orange dashed line here. And then the two cavities that you can see along the side, the teal one on the top is for the boom to be deployed out of. And then on the bottom, because we want to verify deployment, that's our camera viewport. So this kind of underlines the importance of a proper integration when you're doing satellite design and really any complex system design, where not only did we have to factor in outside considerations like surface roughness and fit and tolerance for deployment, but also all of the internal qualifications and requirements from other parts of the satellite that are currently being built. So as I mentioned, we did a manufacturing test after the first revision, and that encountered some issues because of the way we approached it. So the first design was a single piece, where the middle would be cut out of the cube of material. And we wanted to approach that with a water jet, but that caused a lot of difficulties where we ended up with inconsistent corner radii, just out of spec surface roughness, so it would catch in the deployer if we tried to deploy it in that condition. And then also the water jet would divert as it traveled through the material while it was cutting, so we would end up with inconsistent material thickness all the way through the part. And then on top of that, you end up with a square tube that you need to machine both the interior and the exterior from, and that was just going to be a very difficult process overall. So following this manufacturing test, we decided to go with a multi-part chassis that would be bolted together out of basically 4 walls and a couple of other parts. So the second revision that you can see on the right is the 6T plus all of the features of the 1T. So all the ports, the center divider, and all of the other features that usually come on a 1T section. And at this point, this could have been made with no further revisions, and it probably would have worked. The downside here, though, is that the addition of all of the 1T features made it very complicated and really added a lot of extra time to be able to build and assemble it. So our third and final revision involved removing all of the non-necessary 1T features. So almost all of the data ports, almost all of the additional screw holes, the center divider, and a few of the other features. So at this point, the third revision only has one data port that's currently used by NSL to check the health of the spacecraft before deployment, and then also has a maximum amount of internal volume for the deployer and the control board. So on the right-hand side, you can see what a full stack would look like in NSL's deployer, and that would be 6 1T sections in front of our 6T ThickSat. And this is the configuration that will be pushed out of the deployer into space post-launch. So assembly itself was an interesting process and definitely trial by fire. There were a lot of fitments that we need to work through and kind of diagnose. So being able to use 3D printing and other methods ahead of time to check fit and kind of diagnose problems on the fly really helped in making this process a lot smoother. So I think now we will go to Nick Engel to talk about the PCB and control board.
Yeah, hey, thanks, Derek. I'm Nick Engel. I got my bachelor's in physics from Virginia Tech, and now I'm with all these aerospace engineering nerds seeking a master's degree. I was the PCB design lead for the electronics team. I worked with Gustavo, who was the team lead, and then Ian and Stan, who were the manufacturing testing guys that we worked with. So none of us are ECE. We had very little PCB and circuit design experience. So starting, we initially had to start from the top, essentially. We had to first define our science goals. We kind of picked up from the BreadSat team. That was facilitate and monitor the deployment of a carbon fiber composite boom. And then we decided how to achieve them. We wanted to capture an image of the boom upon deployment. We wanted to count the spool rotations with an encoder. And we wanted to measure the spacecraft acceleration caused by the boom deployment with an inertial measurement unit. And those are our 3 redundant measurement styles for our deployment. From there, we had to choose a design program. We chose Autodesk, but that was simply because it was free with a student license, and we hadn't had much experience with KiCad in the past. But KiCad is free and open source for anyone without a student email, so it's much more accessible for those that want to get into this a bit cheaper. We then had to look at our physical constraints, which we kind of pulled in from BreadSat as well. As Derek went over earlier, we had a 6T physical constraint that we had, and we had to fit it within and under the deployer mechanism itself. So we had just a little bit of space to fit this board, and typically board design is an open process. You can design it big and then optimize it down later to fit the space as your design requires. And you can see a lot of these unique and cool designs that people have kind of shrunk PCBs down into by like the pixels dice or flexible PCBs. A lot of these PCBs are very customizable, and a lot of that customizability has to be designed with that in mind in your spatial requirements. In terms of our satellite, we had underneath the payload, we had basically a space enough that would allow us to design a very simple rectangular board and keep enough space to where heating wasn't really an issue between the components. Next, we thought and went through data sheets. Super important for PCB design. Each component will have its own constraints that will affect the design of the PCB. You're going to be looking at maximum, minimum currents, voltages, storage and operation temperatures. All of that good stuff is going to affect how you design your board, and it affected how we designed ours. Then you have to understand circuit design fundamentals, which as an electrical engineering student, this comes naturally, and a little bit in the physics realm as well. But a lot of this had to be learned as we developed, starting late 2020. We iterated and failed and iterated and failed and learned, learning more and more design basics, important things like ground plane intricacies, DC versus AC behavior and their interaction, trace width and length, all played a very important part in our design, as well as just circuit design that was super essential. Then, initially in the project, I thought I could skip out on software skills, but that is not possible with hardware design and PCB design. You have to know software things, coding, at least the communication protocols like I2C, SPI, CAN bus, or JTAG. They all have specific design requirements for their hardware that helps them on their software side. So microprocessors and controllers all are designed with one or multiple communication protocols in mind. The most common of these are SPI and I2C. Most of you will probably know that. But JTAG and CAN bus are, JTAG's older, CAN bus is newer, but they all serve the same purpose of communication in between components, and that is all super essential for design. Moving on to our final flight electronics, it took 5 revisions, 4 to 5 months of just manufacture, design, manufacture, test, fail, learn, and repeat, many sleepless nights, and so we got a full satellite with a working PCB that we're super proud of, but still could use some work. On our board, we have our microcontroller is our STM32 F429ZI. That gives us all the functionality and memory that we would need. We also have our FRAM, our external radiation hardened memory, and our micro SD card slot for large memory bases to keep pictures. And then we have our ArduCam 2 megapixel camera. This is our pictures of the boom. We have our E4T optical encoder as opposed to a magnetic encoder, and our ICM 2602 inertial measurement unit. However, we encountered issues approaching delivery deadline, overcurrent draw from the ThickSat hub model that we were using from our power supply, and we were unable to implement the micro SD card or the IMU or our FRAM. However, the internal memory of the STM32 was more than enough to take a picture, send it, delete, take a picture, send it, delete. In the future, we are going to apply both the micro SD, the IMU, and a new, easier to communicate with FRAM unit that uses SPI rather than 44 separate pins to communicate data and address lines. So we'll have all the same capabilities and more with our F revision going into the future and future ThickSat mission possibilities. Now we're going to kick it off to Minzin to discuss manufacturing.
thank you, Nick. Let's see. So my name is Minzhen Du, and I'm in charge of the deployer flight hardware fabrication and integration. And this is the deployer we use for our prototype deployer we use for preliminary testing. However, for the flight hardware, we need to make sure that the material we use is vacuum compatible. For example, this orange material here on this prototype is not vacuum compatible. It's a high outgassing weight. It has a high outgassing weight under vacuum, which means some composition of the material on the surface can vaporize quickly when exposed to vacuum, and these can be harmful for the sensors on the spacecraft. So initially, we considered the option to 3D print this original prototype model with a low outgassing filament made out of Altum. However, Altum prints at a relatively high temperature and requires specialized printers to minimize the deformation of the finished part as the model cools down. And the 3D printer we have access to were not suitable for printing such a structure with a large surface, such as the sides here. Which brings us back to this picture we saw earlier. We decided to break it down into smaller pieces and machine them separately out of Altum and Darwin, which much like what we did into the chassis, this becomes a simple 2D contour machining process, which can be done in-house with a desktop CNC machine. And these are the additional battery mounting brackets machined out of Darwin. And a few pictures taken throughout the fabrication process. This was one of the sides holding the servo. We ended up using Altum, which on the right here you can see in this color, because we want this particular part to be as rigid as possible. And this was one of the lists for the battery mounting brackets with engravings of our initials and the ThickSat logo. And the right-hand side is the aluminum side cover piece used to secure the ball bearings in place so they don't fall out of the deployer during the vibration of the launch. And speaking of the launch, let's switch over to Dr. Black.
Great, thanks, Minzhen. And so hopefully everybody now kind of has an idea of the size of what we're talking about, the size of our particular ThickSat experiment, right? We're about a 1U CubeSat size that is attached to the ThinSats that are now getting ready to launch on NG-15. So we'll hand it over. I think, Madison, you can transition over to the live stream, and then we'll be back after this for some more of your questions. So thank you all for
Christina Halona. Thanks for joining us today. But of course, she's going to be busy over these next critical milestones here. Now that we're inside 5 minutes and switch to internal power, the next major milestone is coming up just a little over 3 minutes. We'll begin the auto sequence handoff to terminal count. The computers will take over, and Antares will be counting down with those computers automatically to launch, targeting again 12:36 and 49 seconds p.m. Eastern Time.
LC priming verified. Roger that. MES1 will check 412. And we're now on terminal count. Phase 3 dynamic limit will be active at T-minus 3 minutes.
3 minutes and 15 seconds until launch. Terminal count targeting that exact liftoff time, 12:36 and 49 seconds. Tanks will be pressurized at about T-minus 40 seconds, and we'll be counting down to T0. Everything's good for launch today.
Auto sequence start. Audio and bus voltages and currents and nominal. Copy all, LAC 1. GNC1, step 418, verify ready for nav mode.
LC GNC1, orb nav, ready for nav.
And Ops 2, you go to switch to nav.
LC Ops 2, switch to nav.
nav telemetry verified.
Copy all. Check 419 and check 420. TLM, you can switch link 41 to open loop.
LCTM copy. Link 41 open.
T-minus 2 minutes on my mark. Mark. T-minus 1 minute, 30 seconds. T-minus 1 minute on my mark. Mark. T-minus 30 seconds. T-minus 10. 5, 4, 3, 2, 1. We have engine ignition.
Main engine start. And we have liftoff up in Harry for NG-15 mission, the Wallops Flight Facility. Engines are at 100%. Attitude, core pressures, and vehicle subsystems are nominal.
The SS Katherine Johnson takes flight on this, the 59th anniversary of John Glenn's Mercury flight, carrying 8,000 pounds of cargo to the International Space Station. Good performance on the first stage so far.
Engines at 100%, all systems nominal. Stage 1 continues. Nominal performance. Engines at 100%. Good core pressures. Engines remain steady. Attitude nominal. Max Q. Attitude nominal.
First stage passing through the area of maximum dynamic pressure on the rocket. 90 seconds into the flight. This first stage burns for a little over 3 minutes, 3 minutes 18 seconds until main engine cutoff.
About 90 seconds to stage 1 burnout. Attitude nominal. Engines at 100% and steady. T plus 2 minutes. All subsystems continue in nominal performance. All subsystems are nominal. We'll be ready to shift down to 80% on the engines at 170. Start of slow throttle down.
Throttling down at 3 minutes into the flight, main engine cutoff coming soon.
Throttle down to 55%. Main engine cutoff.
We have MECO, and Terry's entering into a coast stage. Fairing separation will occur about 30 seconds later. As we lose sight of the vehicle, now switching to animation. Some controlled firings on the interstage of the rocket.
Attitude nominal. Good separation. "20 seconds to stage 2 ignition. All subsystems nominal. Fairing separation. Interstage separation.
Confirmed fairing separation and interstage.
Stage 2 ignition.
Stage 2 ignition confirmed. Stage 2 is a solid rocket motor, burns for about 2 minutes 44 seconds.
Stage 2 will continue to burn for another approximately 2 minutes.
All right, great. So we got it up and launched, and it'll be rendezvousing with the space station here in a couple of days, and then we'll be dispensing some of the other experiments, including ThickSat, within a few days after that. We wanted to show, I think if we can bring up a couple of other slides on the sort of future of the experiment and our future plans for what we're going to do to create a series of experiments where we can launch these kinds of space experiments regularly. We have a whole variety of flights that we do at Space at VT with several of our partners, and on a fairly regular basis. Just want to thank here, I think, wanted to reiterate our thanks to several of our partners at Space at VT and the Hume Center, AOE, ECE, Virginia Space, NSL, Twig Space Labs, NASA Langley, VSGC, and all of the folks who have collaborated on this project. I think maybe we'll hand it over to Gustavo for a minute, and then come back and talk about the timeline after Gustavo gets a chance to speak.
Thank you, Dr. Black. Thank you so much. This project was a big deal for Space at VT Virginia Tech, and the reason behind this was that the challenges the team faced and overcome throughout the design, build, assembly, and delivery of this satellite was incredible. Not only due to the pandemic that we faced during 2020 on our assembly, test, and delivering process, but also to some technical challenges working such complex mechanical deployer for a small volume and a small power budget. So the work with VA Space, to work with VA Space, NSL, TSL, and NASA proved to be substantial and important to guide the students towards this achievement. And I'm so proud that the team put this together. We have seen today a great deal of how proficient these students had become from this project, and how they're great engineers from Virginia Tech. And then in total, we had more than 25 students involved in this project in all the phases of the project. Just to give a little example, this project started in 2018 with a group of senior design team led by Brendan Griffin and Dr. Shimpaw. And then from there, the project was transferred to our team, where I had the pleasure to lead this team. And we were responsible for making sure that this project ended up flying in space as a satellite. and and making sure that this mission is feasible was a great achievement for all of us. During this process, almost over 2 years, the team faced many more challenges, and I guess we already saw a bunch of those challenges based on the complex difficulties that that our team just put it here on the presentations. But if I could say something single that was the main challenge of this project, I would definitely say that was very hard to make this complex delivery system for NASA under such a small power budget and a small constraint. So to summarize here, Dr. Black and the ThickSat team, I'm quite proud and being part of this team. The ThickSat is quite a complex satellite with a simple goal to release a structure in space, take a picture and send it back to data. Said all that, I would like to thank you all for the amazing students that participated from undergrads to graduates. I would also extend this thank note to all Space AVT and the Hume Center for their immense support. And of course, our partners at Virginia Space, Twigs, NSL, and NASA Langley. So from all of us students, we thank you all so much, and we'd like to, and I'll be happy to address your questions from now on. Thank you, Dr. Black.
Great, thanks. Yeah, so these were just a couple of slides here on the overall process, and even though things that are going up into space are small, they still take a long time, and we hit a lot of bumps in the road, including coronavirus and other external factors. So this is a great encapsulation of what real space programs at NASA and other places experience. And so we're very fortunate that we were able to involve so many students in that overall process. So I think what we can do is have everybody turn on their cameras, and thank you all for posting questions into the live chat, the live chat on YouTube, and we'll be reading some of those questions here now. And what we'll do is have everybody, as we get those questions compiled here, just maybe introduce yourselves again quickly. So Minzen, you're up on the screen. Just say what program you're in and what your undergrad was in.
Hi, so I'm currently as a master's in aerospace engineering, and during undergrad, I'm also graduated at VT with aerospace engineering degree.
Okay, Derek?
Yeah, so I'm Derek White. I'm currently a master's student in aerospace engineering here at VT, and I got my bachelor's degree in mechanical engineering from Iowa State.
Okay, Gustavo.
Hi, I'm Gustavo Gargioni. I am a PhD student in the aerospace engineering here at Virginia Tech, and I got my bachelor in Brazil in mechanical and industrial engineering.
Great, Shada.
Hi, I'm Shada Doverio. I'm a research associate at Electrical and Computer Engineering Department. So I got my PhD from Mechanical Engineering Department at Virginia Tech.
Okay, Rob.
I'm a PhD student here at Virginia Tech. I also got my bachelor's in aerospace engineering, also here at Virginia Tech.
And Nick.
Hey, I'm seeking a Master's of Science in Aerospace Engineering here at Virginia Tech, but I graduated from Virginia Tech with a undergraduate Bachelor of Science in Physics.
Great, so thanks. Hopefully everybody can see that we have a diverse group of backgrounds here, an occasional cat walking across the video feed as well. And I guess some of the questions have been popping up. So again, thank you all for that very much. I guess maybe the first one that we should start with is when do we expect to get data? How are we going to get that data? And where can folks find that if they want to see the ongoing status?
I think I can address that. So we're expecting data for the next week. It will come through the Global Start constellation under the Virginia Space realm. So And then from there, we're expecting to have the encoder data, which will be the ticks of like the release of the mechanism. We're expecting around like 2,000 measurements from one release. And then also, of course, we're also expecting, if it performs well, at least one picture, but the software is designed to take 10 pictures and transmit 10 pictures in the next 24 hours. And hopefully we'll have all that data and maybe a cool picture with like maybe Earth in the background. That would be amazing.
Great. The next question, I'll kick it over to Dr. Chamberlain if he's still on, was on the boom and on the kind of experiment itself, and if we were planning on being able to retract the boom or just a single deployment, and again, kind of how that ties in with your future concepts for ACS-3 and some of the other boom experiments.
That's a great question, and I believe on ThickSat it's just a single deployment. But and for solar sails, generally we are going to just deploy it all out, because the complication with a solar sail, if you watched that video earlier, is the booms are actually the nicer thing. The membrane that we fold out is sort of a pain to fold up neatly enough that it unfolds neatly in space, and the idea of trying to refold that back into the spacecraft is kind of terrifying. So for solar sails, a single deployment. But for other applications in space, yeah, we would love to be able to deploy and retract. You could think about these booms being used for things like antennas, for probes, for extending tools. Actually, a metallic version of a similar sort of boom was used on Viking, the first lander on Mars that the U.S. put, and it had a tool that extended out and took samples using a metallic version of a boom like this. So applications like that we're looking forward to in the future. So being able to deploy and retract is one of the next things we'd like to do.
And on the structure side, there was a question on the kind of data that you're looking for. So I think we're looking for straightness data. You said, that it's important that after the booms soak for a while, cold soak for a while, that they're still able to deploy. We might be looking for some damage. Are there other kind of specific data and metrics on the booms themselves that you're looking for?
No, you hit the big ones, especially for this mission. If we had all the capabilities and data transmission possible, we'd love to see structural dynamics data. So we'd love to see how it vibrates in space. But that might have to be the next one. So
that's good. That's perfect. Perfect setup.
Yeah.
We'll do that. Yeah. We'll do that next time.
Yeah.
Great. There was a question I think directed at Nick in terms of experience on programming, and if you can talk about some of the challenges that you face with programming, and maybe just kind of more broadly talk about what it's like to be in a physics background and working on and with aerospace and mechanical engineers on a multidisciplinary program.
Yeah, that's a very good question, because there's a lot as a physics major coming into aerospace engineering. I had to catch up with them in terms of languages that we'd learned or programs that we would have to learn, STK being one of those. But in terms of programming, MATLAB wasn't as primarily focused on, but I've had to learn that. Python wasn't a language I focused on, but I learned heavily coming into this project. That took some time to get used to. Learning about MicroPython was a good boon as a tinier, smaller version of Python for microcontrollers. That helped us with programming the board quite a bit. In terms of physics going into engineering, there's a lot of crossover in terms of like dynamics and sort of kinematics and all of that sort of orbital part of satellites. But there's a lot of engineering we don't get in physics, to be lack of a better term. It's how to apply all the fundamental knowledge that we've got that I've had to learn, be that in CAD or programming or simulation.
Yeah, thanks. I think that's a great message, and that's one of the messages that we want to communicate is that it doesn't really matter your background. The folks that are on here all have kind of STEM backgrounds, but there's room for everybody to contribute, and these kinds of missions allow us to involve lots of students from a whole variety of backgrounds, and so we're very fortunate to be able to do that. On that, I guess on that theme, Shada, do you want to talk a little bit about your background and your involvement, and then maybe some of the other capabilities that we have for science and engineering missions at Space at VT?
Sure. So I have, my background is mostly in mechanical engineering and vibrations and controls. And in all of these space flight missions and all of these projects, there are different aspects. So people from different backgrounds, different like electrical engineering, mechanical engineering, aerospace engineering, physics, they all can work together in a team on different aspects of these projects. And, for example, each of these projects have a design aspect. They have like electronics. They need some, work on electronics and also, even vibrations testing, all these different things. So people should gather from different disciplines to complete a mission like this. And so I joined the Space at VT recently. And I think with a mechanical engineering background, people with mechanical engineering background can be involved in designs and structural dynamics and all these sort of things. And here we have a lot of different projects that are going on at the Space at VT. And we have projects about telescopes on the ground station. We have space science missions. And each of these projects are in different phases. And, we also have, we're also working on an evolved version of the ThickSat for future. And I think we can involve lots of students from different disciplines and also some members of the public on each of these.
Great, thank you very much for that. This is kind of an interesting question. I guess maybe we can hand this off to everybody. If there was one other thing that you could have incorporated into the design or into your portion of the experiment, what would that have been? So Minzin, you're in my upper left.
So so for that, I guess it also answers some question about the final assembly process. And during some of the final assemblies, we were trying to assemble the satellite inside the chassis frame structure and then weld it up that way. And if we have to take it down, we have to take out the entire chassis to take it out, and we roll the spool. So I guess one thing I would want to change would be the little gate. If you can see, you remember the little gate on top of the on the end of the spool. We can make that into two pieces where we can screw, we can bolt the piece onto the part that holds the tape. Then we can possibly switch it out, pull it out from the side, easier for spooling it back up and testing.
Great, Rob.
I guess it's mostly just a lot of small things. The deployer design was honestly one of the first things that was really finalized compared to all the other components. And we had to work the rest of the satellite around that. So ideally, I wanted to see if there were a bit more effective designs in terms of roller placement, perhaps using a larger number of smaller rollers. But I didn't want to be too intrusive of the other components on the system, because if that a deployer changed in any shape, now suddenly everything else would have to be moved around it. But otherwise, I'm pretty happy with what we had. I'm just wondering if it could be slightly more optimized.
Right. So those are great points. That we needed something to work, right? And that was the most important thing, was to get the base mission requirements, and that it was important to focus on those, and to have an ability to, if we had extra time or extra capacity, to do a few other of the stretch goals. But doing those and adding components and changing some of the design parameters would have had this effect on all of the other subsystems, right? That we were trying to build. Nick, what about you?
There's so much that I wanted to implement.
One thing.
One thing. Okay. I think it would be expertise. It's the top of my list is probably expertise. In the future, we've just started working with the AMP lab, in the ECE department, and the guys that work there know what they're doing, and they have awesome equipment. And if we had had that when we were developing this, it would have been much smoother. It would have gone faster, maybe even months sooner. If we had that expertise and equipment, I definitely would have been much happier and much less tired.
Much less tired. Okay, Derek.
Yeah, so kind of in the same vein as Nick's, maybe not a mechanical component, but more sustained communication and trust between all of the partners. So especially with near space launch and VA space, we had a lot of great communication, and we found some solutions to problems that were between all of the groups, like maybe disagreements over particular standards, or certain design requirements that NSL and VA space required of us. If we could go back and do it, having more communication and trying to establish more trust early on would have allowed us to take a few more risks with parts of the spacecraft that may have interfaced directly with their systems. And maybe we could have made the chassis out of sheet metal, or made the walls thinner, or had a different deployer design or something like that, where if you go back through to the start of this project, just having a better understanding of all the groups may have helped us get more out of the design in the end.
Yeah, thank you for that. And yeah, we got the opportunity to interact with a lot of different groups. A lot of those groups, I think, were very helpful in terms of modifying the design, but a lot of kind of what you're hearing, I think, and we'll get Gustavo's perspective in a second, were related to the fact that we were doing something for the first time, right? And that we're changing and tweaking the design. We were allowed a lot more volume, a lot more mass. We were allowed to draw a lot more power than the normal payloads that go up. And so we were very fortunate to be able to do that, and to work with VA Space and NSL and all of our other collaborators in a fashion in which we were able to produce not just this one particular experiment, but hopefully a set of capabilities going forward to allow a lot of different experiments to utilize the additional capabilities that we were able to pack into our particular ThickSat experiment. Gustavo, you got anything to add?
I think you got it all. Like I mean, besides the mission itself and getting the data from the mission, I think the great achievement of this team and this project is the communication between our collaborators, VA Space, NASA, NSL, and understanding how to use that communication well in early on the project is key, because what happened to our development is that we learn to communicate with our collaborators in the middle of it, and then but eventually what happened is that most of the challenges we faced they were eager to help us, and they were eager to make it flexible on their end, and that led us to have better solutions for the challenges we were facing. So if you have this opportunity to have these communications early on, you can pretty much like have more time to develop the solutions for your challenges. And I think this is a great opportunity for Virginia Tech, because now we have kind of like laid down the path for how to execute this like small satellite technology test beds for future missions. And I think this is a great opportunity also for the students to hop in and also gain more in terms of like experience and hands-on experience from their engineering education. So I think that covers it all.
Great, thank you. Here's a good question. If the boom is going to be deployed, so it's spooled up, it deploys out, what do we think the impact of that rotational motion and that rotational torque is going to be on the chassis and the rest of the ThinSats? So maybe we'll start with that one. Was that a Derek question?
So I don't have any specific number that would define the rotational torque that's being imparted by deploying the boom. But I would expect the satellite to be tumbling because of this, but I wouldn't expect it to be damaging to any structure. You'd have to be spinning pretty fast, and given that most of the chassis walls specifically are 1/8 of an inch thick aluminum, you'd be hard pressed to destroy any part of the static structure on the satellite. But I think imaging is also an issue with rotation. So I think Nick can answer the like software side of it.
Yeah, so it's definitely going to cause an impact in rotational torque. In terms of imaging, it could cause a problem in where it spins into the light where we can see the boom, or it spins out of the light. All of a sudden you have black boom contrasted to black void. And that is a very bad image for us. So that is an issue, and it would be nice to have data on that, but unfortunately the electronics didn't work out that way. In the next mission, that will definitely be the case, and that data will be very helpful for other projects as well. However, there are software implementations to help us kind of figure out when we're in the sun based on the solar panel voltage, and kind of help us take a picture of when we're in the sun. But yeah.
Yeah, I think that's a good one of the kind of benefits that expanding the capability of the overall bus and avionics on ThinSat, right? That's a way that this particular approach, right, would benefit not just our experiment, but all the other ones that were going up as well on there. So we have a question on how ThickSat changed or affected the teaching for undergrad and grad students. So the original implementation was through an undergraduate, capstone design class. And so we kind of started there. That schedule that we were showing before, those students then graduated, which is great. We want them to graduate, and then we needed a group or a couple of different student groups to take over after that. But this was definitely a case, and I think you kind of heard right throughout that we have sort of the foundation from the design and the capstone class, and we have a good, robust set of capstone designs. I think we have 8 or 10, maybe even more capstone design, spacecraft capstone design groups going this year just in aerospace and ocean engineering. There is a space engineering major in electrical computer engineering, and there are multiple spacecraft or space capstone designs going on in ECE. There are at least 2 going on in mechanical engineering as well. So there's a lot of different, at the kind of undergraduate extracurricular level, a lot of different capstone design and other curricular experience in space. And then we were also able to use this as a particular application, as you heard, to develop our lab capabilities and our space experiment support capabilities. So we were doing that simultaneously to make sure that we could accommodate this particular experiment, and then are also going to use those facilities and processes and procedures and relationships to develop and support additional spaceflight experiments. So that's a great question. What else? Okay, I think maybe the last one that we have here is for those of you who completed undergraduate coursework in a non-aero field, why did you transition into aerospace? Or maybe why were you interested in aerospace and space generally as a topic here, something that you've spent a lot of time on? Do you want to go in reverse order? Why don't we start with Shada?
Okay. So when I did my undergrad, basically, I did my undergrad and master's in mechanical engineering too. So actually, at that time, I didn't have an opportunity to do my bachelor's in aerospace engineering. So I chose a major close to it, mechanical engineering. And then I completed my bachelor's and master's in the same actually major. And after that, in my PhD, well, I had, again, I thought that I could go to mechanical engineering and, for example, work on areas like vibrations. And after that, actually, after I finished my PhD there, I just transitioned to space, just space sciences. And I think it was my passion from the beginning to go to space science and do space research. But at some point, I didn't have the opportunity. And after that, where I had the opportunity, I felt like I can continue my studies, for example, in mechanical engineering, and still be close to aerospace engineering. So I would say I could see applications of my major in aerospace engineering, in space science. So I would say mostly my passion first for space science, and then the application of my studies in the space sciences kind of helped me get into space at VT.
Great, thank you. Dr. Chamberlain, do you have anything you want to add? What's your background?
So my background is all mechanical engineering. I got my bachelor's, master's, and PhD in mechanical engineering, and in actually in engineering design and optimization. So I transitioned out of grad school into loads and dynamics, and was lucky enough to work with a company that was willing to take me under their wing and teach me a lot. And that's how I ended up working at NASA Langley eventually. Is I wanted to become a civil servant and saw an interesting opportunity in Virginia, and so that's how I got into working on spacecraft structures, and why I'm talking to you guys today. So I was going to say, when you first posed the question, I think one of the lessons I think I'm hearing from everybody is that in aerospace engineering, you can bring a lot of background knowledge into play, and it's not a simple rocket design problem every day. You're going to find yourself tackling problems you've never even heard of before, and it's really the background knowledge in physics and math and programming and engineering that you're going to use. And a lot of what you're going to do in this field is new, so you're going to have to apply that to all kinds of strange things.
Okay, Derek.
Yeah, so as a kid, I watched pretty much all the shuttle missions during the 2000s, closely followed Spirit and Opportunity when I was in grade school. And that really, that was like the first big introduction to aerospace as its own field, and not just, engineering in general. And when I went to undergrad, I initially wanted to go into aerospace engineering, but decided that mechanical would have been better because it's such a much more broad skill set and less defined by a particular industry. over the course of undergrad, I ended up taking some classes in political science on like science policy and technology policy, and then also geology classes specifically related to seismic studies around the time that NASA was landing the InSight lander with the seismograph on it. So I got back into aerospace by non-engineering classes and decided that with my skill set, I wouldn't have quite enough to get a job in aerospace right out of school. So grad school would have been the better route to get my hands on actual aerospace work to put into practice.
Okay, great. Gustavo.
Yeah, so shuttle missions. I was a kid watching the shuttle missions in the 80s. And I guess from there, I was always like blowing my mind about like space and stuff. But it was on my, so when I went to the bachelor, I knew it was engineering. We didn't have, in Brazil, we don't have like aerospace engineering there. So I did mechanical/industrial. But there was a seminar that a person, I think it was the mission director from the Pathfinder, went to Brazil to do a seminar there, and I was there, and that was like superb. Like it was a great blowing in my mind. But then eventually the industry caught me, and I went to work in like manufacturing industry stuff. Eventually I had my own company, but the space was always in my heart. And I think for someone that comes from outside the US, I think the best option would be to have a graduate experience here in the US in terms of aerospace. So that's why I hop into Virginia Tech for aerospace engineering.
Great, thank you. Nick.
Yeah, aerospace engineering was always the goal. Back in high school, I was a super robotics science, space science nerd. I was on the robotics team, all that good nerdy stuff. But I had one physics class in high school, AP Physics, and I fell in love. So I decided to go to tech for physics with the hope that I would do well enough to get into the aerospace department grad school. And thankfully I did. And here I am. I did both of what I love, and I'm doing what I love now. So, yeah.
Great, thank you. Rob.
Well, I did actually do undergraduate in aerospace, but I think my primary motivation was actually an interest in astronomy. And I guess I just wanted to like live in a future where we're already like dispersed on many planets, and I would like to help get to that goal. If I can't already live there, I can at least help with what I can with bringing that forward. So the astronomy was the primary motivation, especially if aerospace engineering can help build like massive equipment like large telescopes, or even create spacecraft that could allow us to visit those other planets to learn more about them.
Great, and last but not least, Minzen.
Hi, so similar to Wab, I'm also undergrad in aerospace engineering. So not in the recent days, there's probably not that many twists and turns as the rest of the team members. But in the early years during high school, I actually did not think about engineering. Well, I did think about engineering, but when I come to US, there are two choices: engineering and criminal psychology. So there were two different fields. So I ended up choosing Virginia Tech and end up going with engineering. And then I faced with the decision of mechanical engineering or aerospace engineering. Then I'm basically, I think I don't have like the kind of heritage you guys have with the shuttle missions and the astronomy and the passion like that. But the movie Martian really turned me around into space engineering, because I always wanted to be like that kind of exploring and wanted to go to new places and stuff like that. And throughout my design teams in undergrad years, and I find myself in a place that I like to be someone that has like this toolbox of many skills that I can apply to when I try to solve new projects and going to new projects and space projects or aircraft design projects to make this toolbox larger. And so that's why I go to aerospace. And as Dr. Chamberlain said, it's an area that involves many fields, and that's what attracted me here. And I want to keep going, and I want to eventually possibly go to Mars.
Great. Well, thank you all for joining. Thank you all for all of the questions. Please go to space.vt.edu and aoe.vt.edu and look up any of the other of our collaborators to learn more and to be able to follow and follow our future launches and launch events and space experiments. Please follow us on social media. I think this wraps up our live stream. Thank you again all very much. And we hope to, again, be able to see everybody live and in person in lovely Blacksburg soon.